All right, in this video, we're going to talk about angle bisectors and proving that an angle bisector does indeed bisect an angle. So if you remember the constructions, when we would construct an angle bisector, we would first take our compass and mark here into the vertex and draw an arc that intersects both parts of both rays of the angle. And so our vertex is A. We'll call this point here B, and this point here C. And then what we would do is we would take the compass again and we would go to each point and create an arc like so to make sure that the arcs intersect each other. So there's our intersection point. We will call it point D. And then if I draw a ray, so small, all right. If I draw a ray that goes through the vertex A and point D, this ray bisects this angle, which means it cuts the angle in half. So therefore, we would say that angle BAD is congruent to angle CAD. Well, how can we take some of the stuff we've been learning and use that to prove that this is true? So let's go ahead and take a look. So what do we know about side AB and side AC? Well, we know they're congruent. The reason why we know they're congruent is because we created them using the compass on the same setting. We made this one arc. So that means that because of the compass that we used, the distance from side AB is equal to the distance from side AC. So we can say AB is congruent to side AC. Now think about what happened here when we made point D. We used again the same compass setting to create these arcs. So we know that the distance from B to D is the same as the distance from C to D. So we can take our straight edge and draw line segments connecting them. So knowing that the distance from B to D is the same as the distance from C to D, and again we know that because the compass was on the same setting to create those arcs, we can say that BD is congruent to CD. So if you look what we've constructed here, we've actually constructed two triangles. And so far we have two pairs of congruent sides. And if we look at side AD, it's a shared side for both triangles. And we know that AD is congruent to itself because of the reflexive property, right? So we say AD is congruent to AD. And so if you look at these two triangles, we see that we have side, 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 because we have three pairs of congruent sides. So we know that these two triangles are congruent to each other, which is our proof that these two angles are congruent to each other. And we know that because of side, side, side. All right, now let's prove a perpendicular bisector construction. So if you remember, the way we construct a perpendicular bisector is we take the compass and we extend it for more than half the distance of the line segment. And then so we're going to go into each endpoint and we're going to draw an arc. From each endpoint, the goal is to have those two arcs intersect each other. So I drew this arc from A, and now I'm going to draw a similar arc from B, or a congruent arc, because I did not change the setting on the compass. So let me go ahead and label these points. Let's call this point C and this point D. And if I take my straight edge and I draw a line segment connecting C and D, this creates a perpendicular bisector. So let's use what we know about perpendicular bisectors to prove that this is true. So, what do we know about the distance from A to C and the distance from B to C? Well, we know that they're the same distance, and the reason we know that is because we used our compass on the same setting to make these intersection points. So we know that the distance from A to C is the same as the distance from B to C. So let's draw our line segments, connecting these points together. Oops, slid a little bit. Don't mind my mistake there. And then so we know that AC is equal to BC. So we'll mark them each with one bar there, okay? Now we can do the same thing going in this direction. The distance from A to D is the same as the distance from B to D because again, we use the same setting on the compass. So draw these line segments. And again, we know that AD is equal to BD. So then how do we know that CD is a perpendicular bisector of AB? Well, we know that because when you have a perpendicular bisector, the distance from any point on that perpendicular bisector is equidistant from the endpoints. So C is the same distance from A as it is from B, and D is the same distance from A as it is from B. So by the converse of the perpendicular bisector theorem, we know that CD is a perpendicular bisector to AB.